Hi, so we are going to talk today about geometric random variables. And before we start, here's a quick little warm-up problem. So is this situation binomial? Why or why not? So take a minute, read this, and think about if this is a binomial situation. You can pause the video. And while you're taking a look at this, homework, some practice with geometric random variables, some multiple choice practice with all of chapter 6.3. And then I'm going to give you a take-home quiz assigned tomorrow and due Monday. So in this situation, in order to check to see if it's binomial, remember we check bins. So first thing, it's binary. Either the marker's red and therefore we have a success, or it's not red and that would be a failure. We have independence because we're sampling with replacement. In other words, when she selects the marker, she notes the color but then puts the marker back. So she kind of like resets the box of markers, and therefore the result of one pick doesn't affect the result of any other picks. Remember, when you list these conditions, you're very specific. Here's the problem. N. It says she keeps selecting markers until she pulls out her first red marker. So I could pull out the first red marker on, the first pick, and then N would be 1, or it could take me 5 picks or 10 picks. So N might be 5, N might be 10 on a different trial. So I don't have a fixed N. So I really don't even have to go any further. I can say that this is not binomial, but let me just check all of these conditions. So my S, same probability condition, the probability of success is 20% because 20% of the markers are red. And again, we're resetting the box every time. So S is good. The N is the problem. So because we don't have a fixed N, this situation is not binomial. And in fact, this is exactly what we call a geometric situation. And you're going to see in just a second. Geometric is very similar to binomial. Really, the only difference is that we're looking for the first success. So there isn't a fixed N. So today, like I said, we're going to talk about geometric distributions. This is the end of chapter 6.3. So if you have mastered binomial distributions, geometric should be pretty easy. But geometric distributions, like we said, very similar, except for instead of a fixed N, we're going to be looking for a number. So we still have this idea of like the situation is binary, there's a success or a failure. We still need independence. And remember, back from binomial, we need independence so we can multiply probabilities. We're looking for the first success, and we need the same probability of success on each trial. So instead of saying bins, so, binomial situations, we check the conditions bins. With geometric, we're going to check bills, B-I-L-S, where L is looking for the first success. So if we have a discrete random variable x and say that x is the number of trials required to obtain our first success, and if that's a geometric random variable and the probability distribution of success is on our nth trial, is a geometric distribution with probability of success p, we can use this notation. We can say that that random variable x is geometrically distributed with parameter p. Notice we only have one parameter because n is no longer fixed, right? In binomial distributions, you had n and p, but now we just have p. And so just like in binomial, a lot of times if a trial is a success, we distinguish that as like having a value of 1, and if it's a failure, the value is 0. So the possible values of x, because we want our first success, we need to have at least one trial. So if x is the number of trials required to obtain our first success, we can't have a value of 0. So the values of x are going to be 0. The values of x are going to be 1, 2, 3, 4, 5, etc., etc. Theoretically, this could go on to infinity. I could keep on picking and picking until I get my first success. So let's look at another example. A game consists of rolling a single die. We're interested in how many trials we will conduct until we roll a 3. Is this a geometric setting? So we're going to check bills. So you're either going to roll a 3, and that would be your success, or not. That would be a failure. So rolling a 1, 2, 4, 5, or a 6 would be a failure. The outcome of each roll of the die is independent. In other words, none of the rolls affect each other. We're looking for our first 3, and we have the same probability of success, which is 1 out of 6 every time. We have a 1 out of 6 chance of rolling a 3 with every roll of the die. So if we wanted to calculate the following probabilities, we're going to kind of just like we did with binomial, we're going to kind of develop the formula for the probability of a geometric random variable. You're going to see this is real simple though. So the probability that x is equal to 1, in other words, the probability that we get our first success on the first trial, the first roll of the die, it's just like I roll a die, what's the probability to get a 3? 1 out of 6, right? So the probability that x is equal to 1 is just 1 out of 6. There's a 1 out of 6 chance that I get a 3 when I roll my first die. Well, what's the probability that x is equal to 2? In other words, that my first success is on the second roll. Well, if my first success is on the second roll, that would mean that the first roll was a failure and the second roll was a success. The probability of the first roll being a failure is just 5 out of 6. And then the probability of the second one being a success is 1 out of 6. Now, the important part is that these outcomes are independent. Remember, just like in binomial, we need this independence so we can then multiply. Remember, and means multiply with our probability rules, but only if we have independence. So because these are independent, I can just multiply these probabilities. So the probability that I get my first success on the second roll is 5 out of 36. So what's the probability that x equals 3? So remember, again, this means the probability that my first success, or in other words, I roll my first 3 on the third roll. So just like I thought about up here, that kind of means I want the first roll to be a failure, or in other words, not a 3, the second roll to be a failure, and the third roll to be a success. So like not 3, not 3, 3. Again, we can multiply, so it's 5 out of 6 times 5 out of 6 times 1 out of 6. Or in other words, 25 out of 216. So you can kind of see this pattern's going to continue. If I want the probability that x is like 7, that's 6 failures and 1 success. So when we have a geometric random variable, we only ever have 1 success. And then we have however many failures leading up to that. So here's my formula for the probability of y number of successes. We're going to generalize. It's just going to be the probability of a failure, which is 1 minus p, to the number of failures, k minus 1, times p, or in other words, just 1 success, like p to the first power. So it's kind of like I have, you know, if I want the probability, like we said, the probability of that y is equal to 7, it would be 7 minus 1 failures. So it would be the probability of failure to the 6th times the probability of 1 success. So the formula is pretty simple. You probably don't even need this formula. You can figure this out without using the formula. But like we said, the probability distribution table here that you can see below is actually infinite. You can see at the end I have like this dot, 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 because I could have my first success happen on the first trial, the second trial, the third trial, the fourth trial, the fifth trial, the sixth trial. And although it's very, very improbable, theoretically, I could keep rolling and rolling and rolling the die and never get a 3, right? So that's why it's important with geometric distributions. I have this dot, dot, dot at the end. And this is what my probability distribution table is going to look like. The probability of my first roll being a success is just p. Second roll is probability of failure just times the probability of 1 success. 2 failures and 1 success. 3 failures and 1 success, etc., etc. So the name geometric random variables, because it comes from the fact that these are the terms of a geometric sequence. Hopefully you remember your sequences and series, and if not, don't worry about it. But just fun fact, that's where the name comes from. So let's look at a problem. Mr. Lochelle's class decides to play the Lucky Day game. A student will be selected at random from your class and asked to pick a day of the week. Then your teacher is going to use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random and repeat the process. The game continues until a student correctly picks the lucky day. So let y be the number of homework problems that the class receives. Find the probability that the class receives exactly 10 homework problems as a result of playing the Lucky Day game. So remember, before we use any of these formulas, we need, and I mean, I know at the top of the page it says geometric random variables, but we still need to prove that this is a geometric situation before I use that formula. So I can say that x, actually I should say y. I was a little inconsistent here, so pretend that's a y. So y has a geometric distribution with probability of success 1 out of 7. There's 7 days of the week, right? So you have a 1 out of 7 day chance of picking the correct day. And this is because of bills. It's binary. A student either picks correctly or not. I, independence. Each student's guesses are independent because the day is chosen randomly. So in other words, what one person guesses, if they get it wrong or right or wrong, that's not going to affect the next person's guess. We're looking for the first winner, and we already said the probability of success is 1 out of 7. So the probability that y is equal to 10, that means we would have 9 people get or guess incorrectly, and then the 10th person guess correctly. So the probability of failure, which is 6 out of 7 to the 9th power, times 1 out of 7, which is the probability of success. So about a 3.5% chance of going through 10 people till we get a winner. Now, here's the question. Find the probability that y is less than 10. So we already are determined that this is geometric, so we know we can use that formula. But the probability that y is less than 10 would be the probability that y is equal to 1 plus the probability that y is equal to 2 plus the probability that y equals 3, etc., all the way up to the probability that y equals 9. This would be a lot to type in your calculator, right? But this is the formula that you would write out. You have to write all this work out. Your answer is 0.75. I'm going to show you in a second how you would find it in the calculator. But that tells us that there's about a 75% chance that the class will get fewer than 10 homework problems by playing this Lucky Day game. So speaking of, here's how you use the calculator. So kind of like with normal distributions on the calculator and with binomial distributions, we're going to talk about geometric PDF and geometric CDF. So if we want the probability that x equals 10, we're going to point, so geometric PDF, to a specific value. So PDF points to a value, CDF accumulates value. So CDF, remember, accumulates value up to and equal to that value that you enter, that x value that you enter. So if you want the probability that x is less than 10, you actually need to kind of think about that as a less than or equal to. That's equal to the probability that x is less than or equal to 9. So you would have to use your 9 as your x value there. Oh, wait, let me go back a second. So I'm just going to show you, let me pull up the calculator real fast. So again, to get here, I'm at the home screen. I can go second distribution, which is on top of the bars. And here's like my normal PDF, normal CDF, inverse normal. We used all that stuff. We'll use some more of this stuff later. Here's our binomial PDF and binomial CDF. I'm going to keep going. And here's geometric PDF, geometric CDF. Whoops. So if I wanted the probability, like with the one that where we roll the die, if I wanted the probability that we roll a 3, we get the on like, I think we said the 10th roll. So the probability of success was 1 out of 6, right? And if I want to know the probability of getting the first success on the 10th roll, it was 3%. Okay. And then this problem about like the lucky day, let's go to this one and do second distribution. And I can actually scroll up, and that kind of gets me back to the bottom. So geometric CDF, let's find this probability. The probability of success here is 1 out of 7 because there's 70s. And if we want the probability that there's less than 10 questions assigned, remember that's, I have to use my 9 as my x value because that's x is less than or equal to 9. Hit enter, hit paste, hit enter again, and that's where we get that 75%. So the calculator is like real similar to how it worked with like the binomial distributions too. Okay. So formulas for mean and standard deviation. So just like we did with normal distributions, with binomial distributions, the same with the geometric, we're going to describe the geometric distribution. We need to talk about shape, center, spread, SOCS, right? So let's start with shape. I'm going to link to this website here. And so let's start with rolling the die. If the probability of success is 1 over 6, right? This is what my distribution would look like. So if we made that probability distribution table and then made a histogram from all of those values, these are the probabilities of each number of successes. Now, if we played the lucky day game, the probability of success was 1 out of 7. This is what my histogram would look like. You can see they're both really similar. They both have that right skew shape. So now let me find, or let me look at a histogram that has probability of success of, let's say, like 0.5. Notice it looks a little different. It still has that strong right skew shape, but in this case, my x-axis kind of shortens. Before it went up to like 20 or whatever it was. Now it only really goes up to 8. I only have any meaningful areas. I can't even hover there. It's so tiny. But like you can see 7, probability that x equals 6 is, 0.0078. So these areas are really teeny tiny because the probability of success has gotten bigger. It went from like 1/6 to now 1/2, right? So if the probability of success is bigger, let's say like 0.8, I would expect my first success to happen sooner. So the smaller the probability of success is, the longer it might take to get my first success, right? But eventually I'm going to get a first success. So either way, no matter what my probability of success is, 0.1, 0.9, 0.5, or anywhere in between, 0.5, the shape of these are always right skewed, always strongly right skewed. So anytime you have a geometric distribution and we ask you about shape, it's like an automatic, you can automatically say right skewed. The center, the mean, we can find from this formula. The expected value or the mean of the random variable x, if the random variable is geometric, is 1 over p. And the standard deviation you can find from this formula, square root of 1 minus p divided by p. And let's talk about this mean for a second. Think about it. Going back to, the problem with the die, rolling the die, where we were looking for the first 3, the probability of success was 1 out of 6. So 1 divided by 1 out of 6 is 6. So this tells me the expected value would be 6. In other words, how many rolls would I expect to have to roll until I get my first success? 6. That should kind of hopefully make sense. That's where that formula kind of comes from. All right, let's look at another example. This is the one with the lucky day game. So again, notice this dot, dot, dot at the end. Here's the probability table, the probability distribution table. Here's the histogram. See, it has that strong right skew. So the shape, if we asked you to describe the distribution, you're going to say the shape is skewed to the right. The center, the mean is 1 over P, or in other words, 7. If the class played the Lucky Ducky game many times, they would receive an average of 7 homework problems. And then the standard deviation, square root of 1 minus P divided by P, is 6.48. If the class played the Lucky Ducky game many times, the number of homework problems they receive would typically vary from the mean by about 6.5 problems. Remember, when we talk about interpreting these means and the mean and the standard deviation, it's a random variable. So notice many times, many times. It's not just like the average number of games is set, or the average number of homework problems is 7. No, it's if we play the game many, many, many times, they receive an average of 7 homework problems. And that idea of like playing the game many, many, many times, remember, that's the whole idea. That goes back to what the random variable actually is. All right, so another example, a local fast food restaurant is running a draw 3 get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer has to pay the bill. So let X equal the number of customers it takes to get the first free order on a given day. So calculate and interpret the mean of X. Remember, we can't just use that formula. We need to determine that it's a geometric distribution first, then we can use the formula for mean. So we can say that X, where X is the number of customers it takes to get the first free order, is geometric because we have binary. The card that's chosen is either a 3 or it's not. We have independence because we're going to assume that the deck of cards is reset after each trial. We're assuming that the computer programming kind of resets itself. We're looking for how many customers it takes to get the first free order, and we have the same probability of success. There's 4 3s out of the deck of cards, right? And there's 52 cards in the deck. So the probability of success is 4 out of 52. So calculate and interpret the mean of X. This was just kind of like the setup, right? Now let me actually do the work. So because X is geometric, I can use this formula 1 over P, which is 13. So my interpretation, if the restaurant runs this lunch promotion on many, many, many days, the average number of customers it takes to get the first free order would be about 13. And hopefully that kind of makes sense, right? About, you have, if you look at a deck of cards and you look at how many 3s you have 1 out of every 13 cards is a 3. So it kind of hopefully would make sense to you that the average number of cards, or the expected value until we get our first free order, should be about 13. Standard deviation, again, I already proved that this is geometric, so we can use that formula. So plug in 1 minus P, the square root of that, over P, so 12.49. Again, if the restaurant runs this lunch promotion on many days, that part's important, the number of customers it takes to get the first free order would typically vary by about 12.5 from the mean of 13. That is it for geometric random variables. So again, quick reminder about homework and what's coming up. Thanks for listening.